Hello, everybody. This is Sunday. It's November 7th, and we are moving into week 11 of our online astronomy course. I hope you all survived going off daylight savings time this weekend. You got an extra hour of sleep. So it's Sunday morning, and I'm feeling pretty good this morning. So what lies ahead this week? Well, this week, Module 11 is all about one of the most fascinating stories in all of astronomy, and that is the life and death cycle of stars. You know, stars, like anything else, are born, and we'll find out that stars are born in huge clouds of gas and dust, much, much larger than our solar system. And those clouds of gas and dust contract. Their own gravity pulls them together. And you know that if you compress a gas, it heats up. If you've ever pumped up a bike tire with a pump, you know that pump gets hot just from compressing the gas. And the same thing happened with this collapsing gas cloud. It heated up, and the center became more and more dense to form at the very center a star. So we'll learn about how stars are formed, and we'll learn about what powers these newborn stars. Stars like our sun, we already know from the module on the sun, are powered by the proton-proton chain. You have four protons that fuse together to form one helium nucleus. And that liberates energy and produces the energy that powers the sun. Now, that works great, it turns out, for stars that are, you know, the sun's mass or a bit lower, but for stars that are a little bit more massive than the sun, there's another process that produces the star's energy, and that's called the Cno cycle. C for carbon, N for nitrogen, O for oxygen. And so what happens is that atoms of carbon, nitrogen, and oxygen are built up, and in the process, they change, once again, four protons, four hydrogen nuclei, into a helium nuclei. And again, that is how hydrogen is turned into helium in these more massive stars. So it's a fascinating story, but as these stars are burning, you know, when astronomers talk about burning, they're talking about nuclear fusion, and they use the term burning as shorthand for nuclear fusion. It's not like chemical burning. It's not like wood catches fire. So we're talking about nuclear fusion reactions here. But whether a star is using the proton-proton chain or whether it's using the Cno cycle, there's only so much hydrogen available in the star's core that's available for changing hydrogen into helium. And the star has only a certain amount of time it can stay on the main sequence of the Hertzsprung-Russell diagram, that diagonal line that goes from the upper left down to the lower right on the Hertzsprung-Russell diagram. In fact, the lifetimes pretty much depend upon the star's mass and how much energy per second the star gives off, its luminosity. And you'll learn how we calculate the lifetimes of stars. For instance, our sun will live on the main sequence for about 10 billion years. Now, it's already over a little bit over 4.5 billion years. So the star is middle-aged, and the star is moving into a more advanced age. It turns out that the more massive, brighter stars, you might think they would live longer because they have more mass, but they're using up that mass so fast because they're giving off so much energy that they use that mass up very quickly. So they only may live tens of thousands of years. Whereas the very smallest stars, the M stars at the very lower end of the main sequence, these low mass stars are not very bright at all. And so those are like misers, you know, who are very miserly at burning their nuclear fuel. And so every star that has ever been born is still on, every low mass star, I should say, that has ever been born on the lower end of the main sequence is still there, because these low mass stars live an incredibly long time, longer than the age of the universe. But what happens when all the hydrogen runs out? Well, the star has been changing hydrogen into helium, and that continuous compression of the star causes that material to heat up, and then it's hot enough for the helium to fuse into carbon and oxygen. And if the star is massive enough, then it can get hot enough after the carbon and nitrogen are all gone to fuse higher mass elements and higher elements and heavier elements until you get to iron. And even the most massive elements cannot fuse elements heavier than iron. You can't fuse nuclei heavier than iron and get energy out. You have to put energy in to get them to fuse together. And so iron is the end of the fusion story. Well, then what happens? Oh my gosh, there's no nuclear reactions going on in the center of the star. And that may happen at different points, depending upon the mass of the star. And what happens next is the death of the stars. Low mass stars, and the sun is a low mass star, low mass stars can only ever fuse helium into carbon and oxygen. And that's as far as it goes, and that's as much as they can fuse. And what happens is that the center core of the star, which is made of carbon and oxygen, becomes very small and very dense. And meanwhile, the outer layers of that star, that low mass star, puff off to form a planetary nebula. And that is what you see right behind me. This is a planetary nebula that has been ejected by this dying low mass star. And so what you're looking at right there is the core, the oxygen, the carbon oxygen core of that dying low mass star, and that is called a white dwarf. This white dwarf star packs about the mass of the sun into something that is the size of the Earth. Now, if stars are more massive than the sun, much more massive than the sun, they can burn heavier and heavier and heavier elements. And what happens then is that when they reach the end of their fusion chain, those stars collapse because there's no more pressure inside to hold the star up. So gravity just pulls that star together and a dense ball of neutrons forms. And all that infalling material bounces off of that dense ball of neutrons, bounces back out again, and that is what we call a supernova. So high mass stars are going to end their life by exploding as a supernova. And we'll learn all about that. It's a fascinating process, and it's a very important process, because as these stars explode, they spread all of the heavier nuclei, all the heavier atoms that they've created in their centers throughout the universe. And those heavy atoms end up in our bodies. And so we are literally made of atoms that were manufactured inside stars. The carbon, the nitrogen, the oxygen were all created, were all manufactured inside stars. The hydrogen, which is the fourth of the four elements that are really the building blocks of life, hydrogen, carbon, nitrogen, and oxygen. The hydrogen is primordial, and it was made in the Big Bang, and we'll learn about that at the very end of the course. But the carbon, nitrogen, and oxygen in our bodies, and all the other atoms too, were made inside stars or by stellar processes. Now, neutron stars can make these big balls of neutrons, are called neutron stars, and they pack the mass of a sun or two into something that is the size of Ogden. They're about 10 kilometers across, 10 or 20 kilometers across. So they're very small, extremely dense. They have super high gravities. I mean, it's incredible to think just how massive these stars are. You couldn't even stand up on a neutron star. You would just be squished into a little puddle. Now, the highest mass stars are also going to have fusion in their centers. That'll go all the way up to iron. That's the heaviest element, remember, that can undergo fusion or that can be created by fusion. And then those most massive stars run out of fuel for their fusion. Pressure is gone from the inside. The star collapses. A neutron star forms, but even that can't hold up. And what happens is that you have a supernova, and that ball of matter in the center collapses to form a black hole. So in this module, you'll also learn about those most amazing objects in the universe, black holes. A lot of cool stuff here. And you shouldn't think as white dwarfs and neutron stars and black holes as just being the end and being not interesting in themselves. Because white dwarfs, for instance, are made of carbon and oxygen, and as they cool, they crystallize. And so they're going to be, those crystals of carbon are called diamonds. And so we're going to have diamond-like, huge objects floating around in the sky as large as Earth. Neutron stars, we'll find out, you know how an ice skater, as she's doing a scratch spin, pulls in her arms and she spins really fast. Same thing with these neutron stars. As they collapse, as the center of the star collapses because the pressure is gone, they spin really fast. And we can see these rapidly rotating neutron stars. They form objects called pulsars that give out regular little radio pulses that sometimes pass by Earth. They're like lighthouses, and as they go around, they'll send a pulse toward Earth and toward Earth and toward Earth. And so we see these radio pulses from these rotating pulsars. Also, two neutron stars can orbit each other. And if two neutron stars orbit each other, they can merge together. And that creates a huge explosion, much greater than anything we know of. It's called a kilonova. And a lot of the heaviest elements are created in these kilonovas. So you have atoms in your body that were created in merging neutron stars. And black holes, of course, can serve as powerhouses. We'll learn how black holes are essential for the formation of galaxies. There's one in the center of our galaxies. We'll learn all about the important role in astronomy played by black holes. Now, let me back up a minute because I want to talk about something else, and you'll have to read about this in the introduction to Module 11. Because as stars age, as stars evolve, and when an astronomer means evolve, they simply mean the star ages. It's not like in biology where evolution means you're through selection of desirable traits, you're creating new species. Evolution, stellar evolution, means they're just looking at the changes in the star as it ages. And what happens to some stars, as they age, they become unstable and those stars pulsate. Their surfaces move in and out very rhythmically. And as they do so, they grow dimmer and brighter and dimmer and brighter. And the time for one bright, dim, bright cycle to go from bright to dim to bright cycle is called the period of the star. And a remarkable woman named Henrietta Swan Leavitt, about 100 years ago, discovered a period luminosity relation. And that is by looking at a star's period, by just measuring the period of a star with your watch, how long it took to go bright, dim, bright. By measuring that period, you could tell what the star's luminosity was, how bright the star intrinsically was out there. Now you can also look at a star, that star in the sky, and see how bright it appears in the sky, dimmed by distance. And by comparing how bright the star really is from this period luminosity relation to how bright the star appears, just by looking at it, we can figure out the star's distance. And so these pulsating variable stars are how we know the distances to the farthest object in the universe. And you'll learn all about that. So, super cool things to learn about in this module. And there's a great sight that you can see this week in the sky. So let's take a quick look at that. I want to share the screen here, pull up Stellarium, take a look and see what we have. And this is set for, it's November 8th, so this is Monday night, but you can see this, variations of this, any night this week, Monday, Tuesday, Wednesday, Thursday at least. And here we are on Monday night, and if you're out, this is around 8:15, so you can see there's still a glow here in the western sky. The sun has recently set. Venus is still in the sky, and so you can see there's a straight line from Venus to the moon, to Saturn, to Jupiter. And I already told you in a couple movies ago how this is the plane of the ecliptic. And if you just put your arm, hold up your arm in the sky to go along those planets, this is the plane in which the planets orbit our sun. So right now the moon has just passed by Venus. And if we take a look at what things are going to look like the next night, Tuesday night, the moon will be approaching Saturn. Then by Wednesday, it's past Saturn. And by Thursday, it's actually passed by Jupiter, and it will keep on going. The moon is moving eastward through the distant background stars. So it's really cool to see. Now, next week, I'll also be telling you about the upcoming eclipse of the moon. The whole thing is going to be visible from all over the United States. We'll have a great view of it here in northern Utah or wherever you may be. You'll have a great view of it. And that's going to be, it starts in Utah at least, on the evening of November 18th and goes into the morning of November 19th. I'll be telling you more about that next week. So this is just fascinating story here about the lives of the stars, and they are intimately connected with our lives. We owe our lives to the stars because our very bodies are made of material that's manufactured inside stars and by stellar processes. So I hope you enjoy learning about that, and I'll look forward to seeing you next week. So if you have any questions about this, as always, ask me a question on discussions, send me an email. I can set up a Zoom meeting, we can meet in person. So whatever works for you. But have a great week, and I will see you next time. So see you next week. Bye-bye.